Let's see this example. Now let's say we have a relation which is having a, b, c, d, e, f, g, h, i, j. These are all the attributes in that relation, and these are the fd's which are applicable on that relation. Now we want to see whether this relation is in third normal form or not. If it is not in third normal form, we want to get it to third normal form by using decomposition. Okay. And before going for third normal form, we are always following this process of getting the table into second normal form, and from there we go for third normal form, right? So let's first see whether this table is in second normal form or not. In order to check that, you have to observe whether you have to first find out what are all the candidate keys for this table. Now if you see the candidate keys, how to find out the candidate keys is one simple way is find out the necessary attributes that have to be present in the candidate key. If an attribute is not present in the RHS of the FDs, then definitely that is necessary to be present in the candidate key. Just see what are the attributes which are not present in the right hand side. Now A is not present definitely, or let's see what are present and let's tick them, and remaining you can check it easily. So C, it is present in the right hand side, E and F, they are present in the right hand side, G and H, they are present, I, it is present in the right hand side, J is present in the right hand side. Now what are the left out? A, B and D. Therefore A, B and D should definitely be present in every candidate key. It is necessary that they should be present. Why? Because no functional dependency is determining it. If you don't have them initially in the candidate key, there is no way you are going to get them in the closure. Got it? Therefore A, B, C are necessary to be present in the candidate, A, B, D, right? Yeah. A, B, D is necessary to be present in the candidate key. Now let's see if it is sufficient. If it is both necessary and sufficient, then that will be the minimal candidate key, isn't it? Then you will not search for anything else. Now I want to find out A, B, D plus. Then what do I get here? I get A, B, D, and because of A, B, I get C, and B, D is here. Yes, B, D is here. Therefore I can include the right hand side of it, which means E, F, and A, D is here. Therefore I can include the right hand side of it, which means G, H, and A is here. Therefore I can include the right hand side of it, which means I, and H is here, right? Therefore I can include right hand of it, which means J. So all the attributes are covered by A, B, D plus. Therefore A, B, D can be a candidate key. Now A, B, D is a candidate key for this table, and these are the functional dependencies, and any key that you take other than this is going to be a super key. Why? Because this is enough to become a key, and if you remove anything from it, you cannot make a key, and if you add anything to it, it is going to be a super key. Got it? Therefore this is the only candidate key possible, and these are all the key attributes A, B and D. Now let's try to see if there are any partial dependencies in the functional dependencies. Why? We are testing for second normal form. Now if you see this, A, B determines C. So left side is a part of the key, therefore, and right side is a non-key. Got it? Left side is a part of the key and right side is a non-key. So you can say that it is partial dependency, right? And what about this? Left side is a part of the key and right side are non-keys, therefore partial dependency. Now again, left side is a part of the key and right side is non-key, therefore partial dependency. And again, left side is a part of the key, right side is non-key, therefore partial dependency. And what about this? Left side is not part of the key and right side is not part of the key. Actually it is transitive dependency, isn't it? But let's not worry about transitive dependencies as of now. Let's try to get the table into second normal form, then we shall deal with third normal form, because that is the process we are following, isn't it? Instead of directly dealing with third normal form, let's deal with second normal form first. Now how to do the second normal form again here? Take each dependency which is partial and take the closure of it, closure of the left hand side. So AB plus, if I find out AB plus, I get one is AB, because of AB I get C, and then see this BD is not present here, therefore I cannot include its right hand side. AD is not present here, therefore I cannot include its right hand side, but A is present here, therefore I can include its right hand side, which means I is going to be here, right? And H is not present here, so I cannot include it. So check one more time. AB is present here, therefore I am including C. BD is not present here, so I am not including EF. AD is not present here, therefore I am not including GH. A is present here, that is why I am including I from the right hand side, and H is not present here, so I am not including anything. Okay. Now the next one is, after AB, find out BD plus by BD is also a, BD determines EF is a partial dependency, and for every partial dependency take the left hand side and find the closure, right? Because we want to finally make new tables based on this. Now what is BD plus? One is BD. Okay. Now if you see the right hand side, AB is here, but AB is not here, therefore you cannot include C. BD is here and BD is here in the left hand, therefore I can include EF, right? So you are going to get EF. And now if you see this, AD is not present here, so you cannot include the right hand side of it, and A is not present here, so you cannot include right hand side of it, and H is not present here, therefore you cannot include right hand side of it. Okay. And the next partial dependency is AD. Now you have to find out AD plus. Now if you find out AD plus, you are going to get AD and GH. You cannot include C because AB is not present here. You cannot include EF because BD is not present here. You cannot include GH is already included. You can include I because A is already present there, right? So I am including I. Now along with this, I can include even J because H is present there. So I am including J. Okay. And the next partial dependency is A. If I write A plus, I am only going to get A and I. Okay. Fine. Now we have to make these many tables separately. So I am going to take this entire thing, A, B, C, D, E, F, G, H, I, J, and now I am going to decompose them based on all this, right? So A, B, C, I has to be made in one table. So A, B, C, I has to be made in one table, have to be kept separately into one table because of this functional dependency, and for this table the key has to be AB. The key has to be AB, right? And now C and I are gone, so you can just strike it off just to see what are remaining. Okay, whatever are remaining, again you have to keep it in the, leave them there in the main table, or create another table with that and the initial candidate key. Okay, we shall see that. Next one is BD, EF. B, D, E, F. So BD is going to be the candidate key for that. Because of this reason, BD plus is going to be entire thing, and EF is taken away with that. Next one is AD plus is going to give us GHIJ. Therefore AD is going to take GHIJ. GHI is already taken, still no problem, IJ. Got it? Now for this entire table, AD is going to be the key. Got it? Fine, because of this. And next one is A plus is going to take I, and this is the key for that. And I is already taken, no problem. Now what is remaining? I think everything is taken away. So you have to make one more table with ABD. So why is this table important is, this is the table containing the original candidate key for the entire relation, which is ABD. Now why is it important is to see that the decomposition is lossless. Now whenever you want to merge two tables, you will use this table in the middle and you try to merge them. Got it? So if you want to merge these two tables, you cannot merge them directly, because if you see the intersection is going to be B, and B is not a primary key for either of them, therefore it will be lossless. That is why you have to merge these two first. Now the intersection of these two is AB, isn't it? You can see this. See, what is the intersection of these two? AB, which is a candidate key, right, for this one. So it is lossless. What is the intersection for these two? BD, which is a candidate key for this one, therefore it is lossless. What is the intersection for these two? AD, which is a candidate key for this, therefore it is lossless. What is the intersection for these two? A, which is a candidate key for A, therefore it is lossless. So you have to see that this table is present, so that whenever you try to merge two tables, don't merge them directly, you can merge. Okay, what I mean to say is, see, let us say you want to merge these two. Why do you want to merge these two? Because the questions will be asked like this. For a given value of I, what is the value of f? If these two are in the separate tables, then you will not be able to get the relationship between these two, right? Now you have to merge them and then see it. Now not to merge them, if you directly merge them, now since only b is common, the number of values will be very, they will increase, which means some spurious tuples will be added, some extra tuples will be added, because of which the answer you get will be wrong. That is why merge these two first, so that you will get the exact table, and again merge the resulting table with this. Then you can see that the relation between I and f will be same both in the initial table as well as in the decomposed and then rejoined table. Got it? You will not be getting any extra relations that way, extras, these tuples that way. Okay, tuples it means rows. Okay, now let's see what are all the functional dependencies applicable in all of them. So if you see the first functional dependency, AB determines C, it is going to be applicable here. AB determines C. And the second one, BD determines CF, it is going to be applicable here. BD determines CF. And the third one, AD determines GH, is going to be applicable here. And the fourth one, A determines I, is going to be applicable here. A determines I, as well as A determines I is going to be applicable here. And what about H determines J? H determines J is applicable here, right? Now you check this. So all the functional dependencies are again seen this side, therefore functional dependencies are also preserved in the second normal form. Now let's see whether it is second normal form or not. See, you have to again check this. Now see, once you decompose the table like this, once you decompose the tables like this, you should also check that you should again check whether this decomposition is in second normal form or not. Decomposing one time might not guarantee that the resulting tables are going to be in second normal form. You might have to do it several times till you get into second normal form. Got it? So let's check whether these are in second normal form or not. Here I forgot to put A determines I. Okay. Now check this. If you are seeing this, AB is the key and A is the part of the key. Now the part of the key is determining a non-key attribute, therefore again there is a partial dependency here, right? Now whenever there is a partial dependency, what is that you are trying to do? Find out the closure of this on this table using these two functional dependencies. If I find out closure of this, A plus, then I get A plus equal to AI. Therefore decompose this table into two tables, one with AI, which means this I is taken away, and the remaining you just write them there. AB determines C, right? Now for this table, AB is the candidate key, and for this table A is the candidate key, and now these dependencies will be distributed like this. AB determines C will be this one, will be applicable on this table, and A determines I will be applicable on this table. Got it? Okay, now the resulting tables, they are definitely in second normal form, isn't it? Because there is no part of the key, only one attribute is present in the candidate key, therefore there is no partial dependency. Now there is no partial dependency here, because even though there are two attributes here, either A or B are not determining anything, therefore it is definitely in second normal form. These two tables are in second normal form, right? And what about this? And this is also in second normal form, because when all the attributes are key attributes, it is obviously going to be in second normal form, right? Now let's check this one. BD determines CF. So this is the B and D are the candidate keys. Now part of it, either B or D, is not determining anything. Therefore you can say that there is no partial dependency. Got it? So it is in second normal form. Now what about this one? See this? AD is the candidate key. Now either A or D should not determine anything, but if you see this, A is determining I. So this is a partial dependency for which you are supposed to make one more table and split out A plus. Now if I find out A plus on this, I am going to get A plus as AI, isn't it? So again on the same grounds, if I split out A plus, find out A plus, it is going to give me AI. Therefore I have to split the initial table in such a way that AI will go into a separate table with A as the key, and A determines I is going to be there. And anyway we have already made that table, so you need not have this table again. You can delete this here, and whatever is remaining you have to write it here. Okay, so see, this I has been deleted. Now all the remaining is going to be there. So what is it? AD GHJ, right? Now what are the functional dependencies applicable on this? One is AD determines GH, and the other is H determines J, and anyway A determines I has been written over here. So now look at the resulting. AD is the candidate key. Now A or D is not determining anything, therefore there is no partial dependency on this in this one. Got it? So these two tables are also in the second normal form. This is already second normal form, we verified it. Now this one is also in second normal form. Now let's see this. Okay, this is already verified, right? So you need not have this table many times, which means A determines AI is here, here and here. Just have one copy of it and don't include them in the final count of number of tables required. Got it? So at this point all the tables are now in second normal form. Now how many tables are there totally? 1, 2, 3, 4, that's it, isn't it? 1, 2, 3 and 4 tables. 1, 2, 3, 4. Totally, finally 4 tables are going to be present, right? So along with this, isn't it? I have counted even this. So one table is here, and second table, and third table, okay, fourth table, okay, and then the fifth table. Okay, I missed out this. So totally 5 tables will be present in the second normal form, right? Now let's examine whether they are in third normal form or not. So once you get all the tables into second normal form, you have to now check for third normal form. Now what is that we are worried about? We are worried about the trans-to dependencies. Now let's see if there are any trans-to dependencies. In this one there are no dependencies at all, so leave it. Or there are no non-k attributes, so leave it. So what is trans-to dependency? Non-k attribute determining non-k attribute is trans-to dependency. There are no non-k attributes at all here, so leave this one. Now what about this one? There is only one non-k attribute, therefore one non-k attribute cannot determine other non-k attribute here. So we need at least 2 non-k attributes, right? So leave it. Here also same rule. There is only one non-k attribute, so it will always be in third normal form. Leave it, right? And what about this one? Yes, there are 2 non-k attributes E and F, so you need to check whether there is a dependency between these two. Now if you see this, in the FDs, only one FD is there, which is a complete dependency. The entire key is determining the non-k attributes. Got it? And there is no dependency between E and F. So this table is also in third normal form. Why? Because it is not violating the rule, right? If it violates the rule that a non-k attribute determines a non-k attribute, then only it is not in third normal form. Therefore this is in third normal form. Now coming to this, check this. So there are, okay, now the table has been decomposed, so we need to check this table, not that one. Now there are 3 non-k attributes. Let's see if there is any trans-to dependency on this. If you see this dependency, AD determines GH, left side is key attribute, therefore it cannot be trans-to dependency. Now if you see the second one, H determines J, left side is a non-key attribute and right side is also a non-key attribute, therefore it is a trans-to dependency. Now in this case you are supposed to split the table in such a way that all the attributes, you have to find out the left hand side of the trans-to dependency and find out H plus. Now what is it giving? H and J. Now you split the table in such a way that all the attributes this H is determining will go into a separate table, right? So H and J will go into separate table. Now the remaining will be in the original table. So what is it? A, D, G, H. Now this one will be the key for the newly formed table and AD will be the T for the this leftover table. Now what are the functional dependencies applicable here? AD determines GH and H determines J. Therefore, both the functional dependencies are preserved and also the intersection is H, the intersection between these two is H, which is a candidate key for the second table, and so we are also having lossless decomposition. Got it? So now if you observe this table is in third normal form. Why? It is already in second normal form, and now we have eliminated transitive dependencies. This is not a transitive dependency anymore. Why? Left side is a key now. Left side is a key attribute. Therefore, this is in third normal form. All the FDs are preserved as well as it is lossless. So third normal form is also lossless and FD preserving. Got it? Okay. Now this table is made into this, and anyway this table is also in third normal form. So third normal form. Why? Because there is only one non-key attribute. So finally, after I get all the tables to third normal form, how many tables I got? 1, 2, 3, 4, 5, 6. So totally I got 6 tables, right? So 5 tables I got for getting this entire relation into second normal form, and when I had gone for third normal form I got 6 tables. Got it? Okay, now even if you check it, there will be no partial dependencies. Also if you check it, all the functional dependencies will be preserved. Also you can merge all of the tables. At least there is one way to merge all of the tables in such a way that there will be no spurious tuples or extra tuples. Therefore, even this one is lossless. Whatever we did is lossless and dependency preserving, and also in third normal form. Okay, fine.